All right. So we're going to pick up now, starting at slide 21. This is the diagram that we left. We were looking at this diagram, and we were analyzing some of the ramifications of it, particularly relating to what happens under the influence of inheritance. As a reminder, all of these various things that show up at the top, like center and as an attribute, and translate as an operation, inherit, and are found in all of the classes. However, we did say that shape2D at the top is an abstract class, meaning that you can't create instances from that, because there isn't enough information in that class to be able to do anything reasonable with instances of that class. The only thing you can do is make instances of classes further down the hierarchy. In this case, it's classes circle, ellipse, rectangle, regular polygon, and arbitrary polygon that happen to be at the bottom of the hierarchy. However, that doesn't mean to say that in all hierarchies it's only the bottom one. Sometimes you can have concrete classes that are a little bit higher up in the hierarchy. Okay, that's possible. But one thing we can say for sure is that all the classes at the bottom of the hierarchy have to be concrete. You have to be able to make instances of anything at the bottom. Otherwise, that part of the hierarchy is useless. Okay, does that make sense? We said that there were a number of abstract operations like rotate, change scale, get area, get perimeter length defined in shape2D. Okay, what we're saying, we're putting them up here for several reasons. One is we want to make sure that we have implementations of these methods somewhere down below. It doesn't have to be at the bottom of the hierarchy, but by the time we get to the bottom, we've got to have these. And it's also saying that I can create a variable of type shape2D in which will be put instances of any of these concrete classes. And I can then invoke an operation on that variable, okay, such as rotate. Okay, rotate is abstract in shape2D, but by the very fact that I've declared it as existing in that class, what I'm saying is I guarantee that if I have a shape2D variable, I can call the rotate operation, because I know that there will be a method in any object that is in that variable that will be able to perform the rotate computation for me. Okay? So that's a quick review of some of the key things that we looked at. Let's now move on and just take a look at a few more details. This picture here, slide 22, just shows you the effects, the graphical effects of some of the operations. What a bounding rectangle means, for example, and what it means when you rotate an object and still have a bounding rectangle. What it means to translate, to move an object from one place to another, and to scale an object. Okay, so those are relatively straightforward concepts, but I wanted just to show you what they mean. Taking a look at abstract classes and methods in a little bit more of a formal way with some textual description of what they're all about. Okay, so first of all, an operation should be declared to exist at the highest class in the hierarchy where it makes sense. Okay, so if it makes sense to be able to rotate all two-dimensional shapes, then you should put the rotate operation at that level, even if you don't have any concrete method yet. What we're saying is that you will then have implementations somewhere down in the hierarchy before you reach any of the leaves. So you have to think, does it make sense to move an operation to a higher level? Whenever you add an operation, should it go at a higher level? If it makes sense at the higher level, then put it at the higher level. Okay, and as we said, an operation at a given level may be abstract. Okay, lacking implementation. If you can't implement the operation because you don't have enough information in that class, going back a slide for a second, a couple of slides, you don't have enough information to change the scale of arbitrary shapes because all we have is a center. We don't have any information about the positions of the points, or even how many points, or even whether there are points in a circle. We don't have any points at all that are on the perimeter of the circle, for example. So we don't have enough information to change the scale. but it does make sense to change the scale of any shape, therefore we put it at that level. Back to slide 23 again. If you have an abstract operation in a class, then the class must be abstract. The class as a whole must be abstract. So the very fact that a single abstract operation is declared means, okay, class has got to be abstract. In other words, to have a concrete class, all of the methods that apply to that class must be implemented either in that class or inherited concrete methods coming from some superclass higher up in the hierarchy. So in any concrete class, all the methods must have implementations. You can't be left with abstract operations left over in a concrete class. Okay? Any questions? Okay, and following logically from that, if a superclass has an abstract operation, some higher level class has an abstract operation, then its subclasses at some level, doesn't matter what level, but at some level, must have a concrete method for the operation, and by the time you get to the leafs, all the leafs must have all these concrete methods for all operations, and leaf classes must be concrete. It doesn't make any sense to have an abstract leaf class because it's useless. Okay? You can't do anything with it. To be useful, you've got to be able to create an instance of a class, either a class or a subclass somewhere down the chain. Otherwise, there's no point having that piece of hierarchy there. So those are some rules to think about. One of the things I want to say is that this hierarchy we just looked at, the shape hierarchy, is a particularly big class hierarchy. Most object-oriented systems do have some largish hierarchies like that, but the majority of code in systems is actually found in relatively small inheritance hierarchies. The typical depth of inheritance hierarchies for typical average classes is 1 or 2 levels. Okay? And it's very, very common that there's no superclass subclass relationship for a given class. You have class that's on its own and it's doing something relatively simple and there's no generalization. Okay, that's quite common. Depending on the system, it could be even approaching 50% of classes don't have any superclass or subclass relationship. But there will be a significant percentage that at least have 1 or 2 levels. And in any large system, you'll probably find a few decent-sized hierarchies like this. Okay. The more you have in the way of hierarchies, the better reuse you can get, the better polymorphism you can get, and reuse of superclasses and methods inheriting is a powerful concept. Polymorphism is a powerful concept. And so it's useful to see if you can come up with situations where you can create hierarchies. And, of course, abstract classes and methods and all those kinds of things we've just been talking about. But don't overdo it, okay? Don't force inheritance hierarchies on a system when it actually isn't necessary, because it is a little bit of complexity to put these things in. Okay, now we talked a little bit about overriding, the concept that you can have a class which has a method and then a subclass has a method with the same name that in actual fact takes over the functionality at the lower level. Okay? And we're going to talk a little bit about overriding. We'll go back to that big diagram in a few minutes to see an example or two of overriding. There are a number of reasons why you might want to do overriding. One of the reasons is restriction. Okay? If, for example, I had a method that allowed me to change the scale in 2 dimensions, in this case it's scale x, y. Okay, so I'm scaling a certain percentage in the x dimension, a certain percentage in the y dimension. That would make sense for an awful lot of shapes. I can scale a rectangle like that, as long as the rectangle is oriented horizontally, vertically. If it's rotated, it has a problem. But an ordinary rectangle, I can do that. I can do that for an arbitrary polygon, no problem. It just twists it in different dimensions. Okay? So for example, if I had a polygon that looked like this, okay, something like that, okay, these are my points, supposed to be a slight angle there. If I twisted it, you know, so that I was really compressing this dimension, I might end up getting something that looked a bit more like this. So it might look something like that. So I've compressed this dimension here and kept this dimension the same. Okay? So x dimension 100%, y dimension 20%. Okay? So I can do that. But that wouldn't work in a circle, because if I tried to do that with a circle, what I'd end up getting is I'd change that into that. And that's no longer a circle. And so one of the things that you might want to do is you might want to restrict circles from being able to be scaled unless the scaling percentages are equal to each other. Okay? And in that case, you might raise an exception saying, you know, for a circle, the two dimensions must be equal. Okay? And it refuses to do the operation. Okay? Now, later on in the course, we'll see that you have to watch out for things like that. If you start doing too much of that kind of raising exceptions in certain cases, you end up with a lot of extra complexity in your system. And it's best to try and avoid that. But nevertheless, it might be something that you want to do in certain cases. And that's one of the reasons why you might want to restrict when you override. So basically what you'd have is you'd have a scale method in circle that would raise this exception if these two aren't equal, but that would work fine in all the other classes in the system. And maybe a superclass version in elliptical shape would do the scaling job in the default way, and in the circle it would have this exception raising. Another reason to override is you have extra information, you have extra things you want to do in a subclass. We call this overriding for extension. So for example, I might have a debit method in my bank account system, but you might say that savings accounts, you can't debit funds without having an extra fee charged. And so in the savings account, we override the standard debit, and we charge an extra fee for withdrawing money from your savings account. So that would be an extension. Fundamentally, no matter whether you have restriction or extension or optimization, which we'll talk about, the method should fundamentally do the same thing. From the user's perspective, they call the method, and they don't really care which class of object is in the variable. They're calling a method, they expect polymorphism to kick in and choose the method to run. It does the same conceptual thing. So it debits from a bank account. And, oh, by the way, there's an extra little thing that happens in a savings account, but still, from the end user's perspective, from the perspective of the user of the code that's being called, it's still debiting from the bank account, or it's still scaling the shape. Now, in the case of scaling the shape, it doesn't work in some cases. So basically, if we allow that sometimes the scale operation raises an exception, basically, if you're programming and you're calling scale xy on arbitrary shapes, you basically have to say, okay, I will have to prepare myself for the fact that occasionally I can't scale in 2 dimensions. Okay? And so I will prepare myself for the possibility of an exception by having a try-catch block in Java. And as long as I allow for the possibility that any kind of shape might not allow me to scale in 2 dimensions, then with a try-catch block, if I'm not allowed, I'm not allowed, then I still have a consistent operation that, as far as I'm concerned, works consistently everywhere, even though it happens to only be the circles that don't scale in 2 dimensions. Same thing with debiting money from an account. It might be that I raise an exception if I am about to exceed my overdraft limit. Okay? With a savings account, it might not allow me to withdraw money if I would, the debit amount plus the extra withdrawal fee would bring my account to zero, okay? So there might have to be some slightly different logic there. Say I had $20 in my savings account and I wanted to withdraw all 20. Well, there's a $1 fee for withdrawal. Therefore, I have to have $21 in my account to withdraw 20 because I get a $1 fee. And so this extension that does this extra fee would have to take that piece of logic into account too. So 2 reasons for overriding. A third reason is optimization. In optimization, the concept is that the method does exactly the same thing, with no extension, no restriction as the inherited method. But it does it in a more efficient way. Maybe it uses less memory, maybe it uses less computational time. And it's quite often the case that there are algorithms that work in one class that can be done more efficiently because there's more information or there's more rules in that class. So if we go back a few slides to slide 21 and see the circle class, for example, we've already seen that we have a rotate method. Okay, there's a concrete rotate method here. That's not overriding anything because it's abstract up here. There is somewhere down here, I think it was in get bounding rectangle, okay? We had get bounding rectangle in polygon, okay, which computed the rectangle that would be drawn around any kind of simple polygon or arbitrary polygon. Okay, in rectangle, we have an optimization. And the optimization, from the user's perspective, does exactly the same thing, except that it says, hey, if I have a non-rotated rectangle, okay, that looks like this, what is the bounding rectangle equal to? What is the bounding rectangle of that? Itself. So all it can do is simply say, return this, and it's done. It doesn't have to do anything. And so it's highly optimal, right? So what I have is I have a piece of code that says, if, well, in the class rectangle, if orientation equals 0, which means it's not rotated, return this, else, can somebody tell me what the logical thing to do in the else case would be?
Return the get bounding rectangle polygon.
And in Java, how would I write that? What's the keyword that I would use in Java? Super, right. I would invoke the super implementation. So, in other words, I would have a piece of code that says if in rectangle, get bounding rectangle, if orientation equals 0, return this. Else, I would invoke the super version, and that would go look up the hierarchy and find the one up here automatically. Okay? So that's a sort of standard type of way that you would often write code when you're overriding. You often invoke the super version. Once you've done some work, you then invoke the super version to take over and do the rest of the work. That's quite a common programming idiom, they call it. Okay, any questions about that? Okay, if I bring up things about Java like the keyword super that you don't understand, then it's your responsibility to go and take a look at a Java book or some of the Java references that I have online on the website in order to sort of fill in your knowledge, okay? You can also ask your TA during the lab sections as well. Okay, so those are the 3 types of overriding that are sort of classically recognized: restriction, extension, and optimization. But remember, conceptually, all implementations of the same abstract operation should do the same logical thing. You shouldn't sort of extend in arbitrary ways such that the operation logically does something totally different, or restrict in ways that make the operation so totally different that it doesn't follow the same pattern of behavior as it would in other implementations of the same operation. I want to talk about a concept that can be useful in some situations. It's called immutable objects. Okay, immutable objects are objects which, once they're created using a constructor, are not supposed to be changed from that point onwards in their lifespan. Okay, that's an immutable object. And sometimes you want to design class hierarchies where the objects are immutable for various reasons. Okay? The concept can be useful. For example, if I want to allow an arbitrary two-dimensional scaling operation. So I mentioned this whole concept that, gee, if I have a scaling operation on a circle that's in 2 dimensions, that one of the alternatives would be to raise an exception and say, you can't do it. Another alternative would be to decide that all of these classes, or probably all of the classes, or maybe just, in this case, the circle class, would be immutable. In other words, I can't change the circle. But what I can do is anytime somebody calls a method that tries to make a change, it returns a new object that reflects the change. So if I try and scale a circle in 2 dimensions, rather than raising an exception saying can't do it, what it does is it returns something. Can somebody tell me what it might return if I try to scale a circle in 2 dimensions? An ellipse, right. Okay? And if I tried to scale a square, if I had a square on the hierarchy, it would return a rectangle. If I tried to scale it in 2 dimensions and those 2 dimensions weren't equal. On the other hand, if I tried to scale a circle in 1 dimension, or I tried to scale it in 2 dimensions with those dimensions equal, then I could have 2 options. I could actually make the change to the circle, or I could return another circle, which is bigger. Generally speaking, if you do decide to go the role that you're going to have all these operations just return new objects that have the change applied, rather than change the original, then you should probably be consistent everywhere. You should probably say, everywhere I'm going to follow this pattern and make all of my objects immutable, and all of the operations will just return new versions that have the change applied. Or everywhere I should allow changes. Because otherwise you end up with the complexity of people not being able to figure out whether the objects are defined to be immutable or whether they're not. Okay? So you want to be consistent in any kind of design. Consistency is one of the rules of good design. Remember that when we're doing design, and we give these rules that say what you should do and why you should do it, the fundamental reason is because human beings have got to be able to understand your design. I mean, some of the rules apply for efficiency reasons, but a large percentage of them apply because you need to try and make sure that your system is as simple as possible, as understandable as possible, and as easily changeable as possible. You know, we can write spaghetti code, and we can write big, horrible messes if we want to make a program that no human will ever be able to understand. And in fact, there are a few classic examples posted on the internet of code which is deliberately designed to be totally unreadable. You can do some searches for that, and it's kind of humorous to look at some of this code. But in general, we want to do the exact opposite. We want designs that are easy to understand. And so having a mix of immutable objects and non-immutable objects would be difficult to understand. You'd have to try and figure it out each time. And so we want to, if we do choose a style, all immutable, let's stay with that, or not immutable, we'll stay with that as well. Anybody not understand the concept of immutable? Everybody understand it? Okay, the concept is, if you decide to use immutable objects, once you construct an object, you cannot change its instance variables. They're fixed. And if you have any method that makes any changes or tries to make any changes, the return value is going to be a new shape that has the logical change made, but it's a new object. Now, you should all by now have a pretty fair understanding, conceptually, of how the system chooses which method to run. Okay, we looked at a number of examples of the fact that if you call a method that is invoked on a particular variable, that it will use a method that is in the class of the object that's in that variable, or it will maybe call a method that is in a superclass somewhere. This slide 26, is giving us an actual algorithm, that is a conceptual algorithm at least, that reminds us how the process works. Okay? So the process starts by a call being made on a variable. Okay? So calls are made on variables. Okay? And then there's an object in the variable that is supposed to react to that call. Okay? It's best to think of calls being made on variables as opposed to objects, because first step is that that object has got to be in a variable. It could be a local variable, it could be an instance variable, okay? It could be a class variable too, static, possibly, but let's imagine that we're trying to stick with the variables that we want to use a lot, local variables and instance variables. So call is made on a variable, then the system goes and takes a look at the object that's in that variable, okay, which could be of the class which that variable was declared to be, or any subclass of it. Okay, so if a variable is declared to be of type shape2D, then the objects in that variable could be anything concrete that is below that. Okay, now we already said it couldn't be a shape2D object because you can't have instances of shape2D. But it could be a rectangle, a circle, an ellipse, etc. Then, step 1. If there is a concrete method for the operation in the current class, run the method. Okay, so if, for example, we call getBoundingRectangle on a variable that happens to have a rectangle in it, then there is a concrete method right there, we'll run that. Otherwise, check in the immediate superclass to see if there's a method there, so run it. And if, look up in the superclass. And then repeat step 2. Keep looking up in the hierarchy until you find a concrete method. If no method is found, there's an error. Now, it turns out that the compiler should never allow you to get to the stage of step 4 here. In Java and C++, a compiler should be able to tell you there is no concrete implementation anywhere in the hierarchy, and therefore you shouldn't ever get to this point. But there are programming languages, most notably Smalltalk, which have a different model for compilation. The compilation is done in a style where we basically have a type system where there's only one type, and it can't make concrete checks at compile time to be absolutely sure whether there will never be any possibility of finding a method. And so you can have an error situation in those circumstances where it looks up the hierarchy till it doesn't find anything and then says, sorry, no method found for this call. Now, this process is abstract. It doesn't actually work this way in reality, because in reality there are a lot of optimizations built in. Okay, there are lookup tables that are built in to the runtime environment that allow this process to be done much more efficiently. You could imagine that if you have a big hierarchy, you wouldn't want to be looping. Look in the current class, look one class above, look one class above, look one class above till you get to the top. Every time you make a call, right? That would be inefficient. So in actual fact, the implementation of this process is done in a much more efficient way. And it is dependent on the particular runtime version of the language. But in general, this is the abstract way it's done. Questions? Okay, dynamic binding is another key concept in object orientation that basically flows from the concept of polymorphism and inheritance. And this is what basically happens in that last algorithm. That last algorithm is the process of dynamic binding. It is the process of dynamically deciding which method to run. Okay? And dynamically binding is only needed in the circumstance described here. Okay? Both of these conditions have to be true. First of all, there has to be a variable which is declared to have some class that's not a leaf class. In other words, some superclass that has actual classes below it. That has to be true. Okay? If I declare a variable whose type is a leaf class at the bottom, then I know for absolute sure that I can always know, as soon as I call any operation on this variable, exactly what methods will run. Because there's only one possibility. All the methods that are defined in that leaf class. Those are the ones that will run. Or the ones that are inherited into that class. Okay? But I know exactly what they are at all times for that variable. But if I declare a variable that is higher in the hierarchy, then I can put several different classes of objects in that variable. And therefore, at that point, I don't quite know exactly what's going to run. And the second condition that must be true then is that there must be more than one polymorphic method that could be run. Okay, so it could still be the case that I don't need dynamic binding if I declare a variable of at a high level in the hierarchy, but at that level, all of the methods are fixed. There are no alternative methods that are lower in the hierarchy. No polymorphism will actually be invoked. That's possible too. So that both of these conditions have to be true. There has to be a variable that is some class higher in the hierarchy, and there has to be more than one polymorphic method that could be run among the type of the variable and its subclasses. We're going to go back and look now at a few examples, and I'm going to pose some questions to you, and we're going to see if you can understand and make the right decision about what will be run under what circumstances. And these are particularly good questions for examinations. I'm just going to have to go and get an eraser for a second. Okay, these are particularly good questions for examinations to test if you really understand what's going on in the terms of polymorphism and dynamic binding and abstract classes and all the other kind of stuff. All these concepts are wrapped together in this particular type of question. So let's imagine this scenario, and I'm just going to randomly pick a class and then an operation. And I'm going to say, imagine you had a variable of class, let's just say polygon. Okay? And then let's imagine that I wanted to invoke operation and let's be somewhat arbitrary about this. Initially, rotate. Okay? First question is dynamic binding going to be invoked? And second question is, which method? Which class has the method? Okay? So if I have a variable polygon and I invoke rotate, somebody tell me the answer to these two questions. Anybody want to volunteer the answer? Nobody knows. Okay, it's a good test to see if you understand the concept. Okay, in the back there, yes. Okay, so he says that there are two possible methods that could be run here. So I have a variable type polygon and I say rotate. Okay, here's how you analyze this thing then. Okay, first of all, we know that there's a good chance of there being dynamic binding because polygon is a class higher in the hierarchy. Okay, so we have to look for various versions of rotate in this hierarchy. I see a rotate method here in simple polygon, and I see a rotate method here in arbitrary polygon. Right, okay. So if I have a variable polygon and I call rotate on it, I know that it could be, okay, so dynamic binding will be needed because I don't know which of these will end up running. If I have a rectangle or regular polygon, it'll be the simple polygon one. If I have an arbitrary polygon, it'll be the arbitrary polygon one. Okay? And so which class has the method in this case? It's going to be simple polygon. I'm just going to abbreviate simple polygon and arbitrary polygon. Okay, so dynamic binding will choose between the methods in those two classes. Okay, let's take a look at another situation then. Let's imagine that I had the class regular polygon. Okay, regular polygon. I'm just going to abbreviate again. And I call the operation get vertices. Okay, can somebody tell me whether dynamic binding would be used? Anybody? Who thinks dynamic binding would be used? Hands up. Who thinks dynamic binding would not be used? Hands up. Okay, so nobody wanted to volunteer that information. Fine. Okay, why would dynamic binding not be used? It's got to be higher. Yeah, we're in a leaf. We know for sure exactly what would be called. It would have to be a method that is either in this class or inherited from above into this class. But whatever it is, we know exactly what it would be. And we can we can follow that algorithm we talked about to determine what it would be by just looking. The method is get vertices. Do we have get vertices here? In fact, we have it right here underneath the mouse cursor, right at this very second. It's going to be this one. No choice. Okay? And so it's going to be the one in regular polygon. No problem. Okay, let's then say, what if we had a thing declared as polygon? Okay? And again, get vertices was called. Okay? Dynamic binding? Hands up who thinks dynamic binding would be called? Hands up who think it won't be called? Okay, so the rest of you are on the fence, too early in the morning, etc., etc., etc. Fine, okay, so it's higher in the hierarchy, and there is more than one implementation of it. We have one down here, one down here, one down here. We have three of them. Okay, so yes, we're going to have dynamic binding. This is no, this is yes, and we have all three of the classes below: rectangle, regular polygon, arbitrary polygon. Rectangle, regular polygon, arbitrary polygon. Fine. Let's see if we can find a more tricky case. Shape 2D. Oh, as soon as I say shape 2D, what's the answer to the dynamic binding one? Always? Aha. Okay. Under which particular possibilities would we not do dynamic binding in the case of shape 2D? Okay, so and translate has a concrete method. Is there any other translate down below? No. Therefore, we know that will always be the one that will be invoked. Therefore, no dynamic binding. Get center. Do we have any get center down below? No. Here we get vertices. No. And no. Good. Okay. So you're right. No dynamic binding there either. But the instant response is check first, because it's possible that there might be an overriding version of one of these. And if there's an overriding version, you do need dynamic binding, because there is a choice. Okay? And so the polygon get bounding rectangle case is a case where there is a choice. Okay, so if I have a polygon and I call get bounding rectangle, let's just write that one down. Polygon and get bounding rectangle. I've given you the answer already, right? I already said, hey, look, don't jump to the conclusion right away that there's going to be no dynamic binding just because we have a concrete method right here. Okay, because there's an overriding version down here. Right? So, in this case, it could be the get bounding the polygon version, but it could also be the rectangle version. So there has to be a dynamic binding taking place in that case. Okay? So that's a classic exam, especially midterm question. Hint, hint. to be able to answer those kinds of things. Quick marks if you understand the principles, and problems if you don't. But I think most of you probably can get that. Just proves that you have a good understanding of the core concepts of OO. Any questions? All right. Okay, let's move on then to slide 28. Concepts that define object orientation. These are the kinds of things that need to be present in a system, recognized widely in the industry, that need to be present in a system in order for the system to be called object-oriented. The first of these is the notion of objects having distinct identity. Okay? In some traditional programming languages, and in relational databases in particular, there is this notion that data is data, and two pieces of data that look the same are the same. Okay? Whereas in the object-oriented model, we have objects. And they're the things that have identity, and it might well be that two objects have exactly identical data inside them, but nevertheless, those objects have a distinct identity. Now, even if the data that is inside those objects is the same. And in fact, in programming languages that are object-oriented, there's a way of getting access to some kind of pointer or reference to individual objects, and playing around with the reference to those individual objects. Okay? So objects have an identity that goes beyond what data is in those objects. And that's the first concept that we have to have. And that naturally flows from the idea that objects represent chunks of memory. And the concept then is that, well, these chunks of memory have some kind of address, either in random access memory or on disk, that can be distinctly referred to. It might not be a physical address, it might be a logical address, it might be indirect, but there is some kind of an address that's often computed and referred to as an object identifier of some kind. Some programming languages have a numeric number associated with each object that you can compute with if you want. Now, in C++, you can actually take the address of objects. It's probably not a good idea to do that, particularly because you end up with a lot of machine system dependencies if you do. But it's a possibility. The second thing that we have to have an object-oriented system is something akin to classes. Now, they might not actually be called classes. There are a few programming languages, such as Self, that use a slightly different paradigm, where they have prototype instances, as they're called. But there has to be something that has the role of the class, that contains methods, and acts as a template or model for building instances. And in most programming languages, they're called classes. And certainly in C++, Java, and Smalltalk, which are the three most widely recognized OO languages, the concept is basically the same. So that's code organized using classes, and each describing a set of instances. Pretty clear there. Then the third concept that must be present is inheritance. We've talked about that in some depth. And the fourth concept is polymorphism. So you've got to have all these things, and then you can say, yes, my system, my programming language is object-oriented. Any questions? All right. In addition to this, there are a number of other things that flow from having polymorphism and objects with identity and many of the other concepts. And one of these is abstraction. And there are many different kinds of abstraction. In general, abstraction is the notion of being able to look at something without having to see all the details. Being able to look at a view which is a simpler, higher level view where less important details are not present to confuse you, right? There's also the notion of representation. The abstraction is a representation of one or more things which are more concrete in some sense. Abstraction is a fundamental principle throughout all of computing and has existed since the early days. In fact, the very fact that you have a piece of data in the system is in some sense is an abstraction over the real objects that that data represents. So in the object-oriented world, among the kinds of abstractions we have are the object representing something in the world. It might be representing something physical, like a student. It might be representing something that's more logical, like a course. I mean, this course is not a physical thing, right? It's a logical thing. But you can have objects representing that as well. And we still consider those as things in the world, even though it's a logical thing. Sometimes people, in fact, sort of talk about objects as being the things in the world, but I personally prefer the view to say that objects are data, chunks of data in the computer that separately represent the things that really exist in the world. And I like to separate that view. Then we have another abstraction, the classes, representing a set of objects. So a class is an abstraction. It gathers together information and gives you a view of the structure and behavior of a set of objects. So you don't actually have to deal with the details of each individual object. You just look at the class level. The superclass is an abstraction of a set of subclasses. Okay, and the subclasses are going to have more detail. The superclass is going to be having less detail, and especially if it's an abstract superclass, it's going to be setting out some kind of template for the kind of things that will have to be implemented in the concrete classes below it. The interface, which we'll talk about in a while, is an even more abstract view. Okay, the interface is explicitly saying, hey, we're only going to define a set of operations. We're not even going to give any concrete implementations of any of them. But it's the same idea. It's an even more powerful abstraction. An operation, as we defined it in this course, is an abstraction over a set of methods. Okay, so an operation, I'm saying, well, it has a name, and it has a specification. You can specify abstractly what it means to compute the area of something. Okay, and then the methods are concrete implementations with the detail that comes in. And then we have attributes and associations, we talked about briefly in the last lecture, that are abstractions over the concrete instance variables that implement them. So abstraction is a powerful concept. It allows us to think in simpler terms about the system that we're developing. If we didn't have abstraction, we had to deal with the bits and bytes, every single bit and every single byte, we would never be able to write programs of any complexity at all. Now imagine if we didn't have objects, we wouldn't be able to, we might have to be dealing with methods that were purely procedural and using the procedural paradigm, and bits of information about each student would be scattered throughout the program, and we'd end up with more complexity. If we didn't have classes, well, then we lose any of the benefit of polymorphism and inheritance and so on. If we didn't have superclasses, well, yeah, we lose polymorphism and inheritance. Classes just lose the whole notion of the grouping together a set of methods and using data abstraction as the primary means. Superclasses give us polymorphism and inheritance. Operations give us polymorphism over a set of methods. Attributes and associations allow us to draw diagrams in a more abstract way, without having to worry about the detailed implementation of the actual data that's declared in the instances. We can sort of list the names of things and draw lines, as we'll see later on. Any comments? Modularity, then, is another key concept. Modularity has been around since the early days of computing in the 1950s. The classic module was the subroutine, the function, procedure, name it what you will. Now we use the word method inside a class, but that's the classic one. Classes themselves, however, are also a kind of module at a higher level. And packages in Java are another kind of module. There can be other kinds of modules as well developed. It can be libraries, jar files, things like that. And the notion of encapsulation. The notion of encapsulation is closely related to some of the other notions, some of the abstraction notions that we talked about. Encapsulation says that I am putting details inside a physical package. So I'm writing, for example, encapsulation in context of a method says I've got an algorithm inside my method. But when I'm actually using that method to write other code somewhere else, I don't have to look inside the method I'm calling. I just see its signature, I see its specification, maybe I look at its Java doc description, and I call it, and I don't have to look inside. Okay, so it's closely related to abstraction. The abstraction and the encapsulation together give rise to information hiding. Information hiding is the concept that human beings have a very limited capacity to understand things. We can only work in our consciousness with a few pieces of information, a few chunks of information at any given point in time. You cannot possibly hope to consciously maintain a large array of information about a computer system. And even if you become an expert, and a lot of the information in the computer system is in your long-term memory, you still, once a program becomes millions of lines of code, cannot hope to be able to memorize the function of every single line of code in the system. And so in order for human beings to be able to deal with software, a lot of the information that is in that software has to be hidden. We have to be able to look at a view of the software which is just what we need to know, just when we need to know it. And all the other information is hidden from our view so it doesn't confuse us. Okay? Dave Parnas, who was until very recently a professor, leading professor at McMaster University in Hamilton, was one of the grandfathers of software engineering, and he's now moved to Ireland, or will soon move to Ireland. He's the father of this concept of information hiding. I mean, people intuitively might have had a feeling for information hiding, but when he came out with the concept, everybody says yes. And from then on, programming language developers have always said, let's try and make sure that we build proper information hiding into our systems. Any questions? All right, let's now take a step into a lower level of abstraction. We've been talking at the high level of abstraction in terms of class hierarchies. Okay, now I'm going to jump down and talk about Java, the programming language. I'm not going to, however, give you a complete introduction to Java. You should have that already. What I'm going to do is I'm going to remind you of some of the key points, some of the pieces of knowledge that might be a bit obscure or you might not be totally confident with, that will be important nevertheless later on in this course as you do the work in the simple chat system and the client-server system and so on. Some people might say, well, why am I getting into this low level when I'm giving a course in software engineering? Well, I'm of the perspective that software engineering covers all levels of abstraction, all the way from high-level requirements down to the deep depths of code. It's all software engineering because software engineers, in practice, do programming. Okay? I mean, some people are of the view that if you're a software engineer, all you're going to do is project management, software architecture, and related high-level activities. And indeed, that's what some do. But the profession of software engineering as a whole does encompass all the way down to programming, in my opinion. Okay? And should. It's just like if you're an electrical engineer, some people say, well, electrical engineers should do high-level design using floating point gate arrays and things like that, and forget about learning how individual resistors and transistors and things like that work. But if you're learning electrical engineering, you certainly learn how basic circuits work, even though you may end up working at a much more abstract level. Okay? If you're building bridges, you're going to learn an awful lot about soil mechanics and about various aspects of bridges that you might end up not actually practicing in because you might end up picking designs from a catalog. But you still, in order to be able to do a good job of picking designs from a catalog, you do need to understand the low-level principles as well. So even if you're a software engineer that's primarily doing requirements and software architecture at the very abstract level, you can't really make good decisions about those requirements and that architecture and the project management issues if you haven't at some point in time become a good programmer too. So software engineers should become good programmers. Some of them will always continue to do good programming. Some will focus primarily on the programming side, which is often called software construction. Many will do the spectrum. In the high-tech companies that I've worked for, and in the government organizations I've worked for, which includes the government of New Brunswick, Nortel Networks, and Mitel Networks, okay, all those organizations, people developing software, do programming, do requirements, do design, and take part in project management. And the best project managers do have programming background. So that's why I'm of that firm belief. Okay, so getting on to Java then on slide 30. The history of Java, well, the history of object orientation is that the first OO programming language came about in about 1967 with the Simula language. It developed in Norway. And Simula, by the way, the descendants of Simula still exist today, although they tend to be restricted in use to Scandinavia. In 1980, Smalltalk came along. Late 1980s, C++. Okay, Smalltalk, Xerox PARC, very famous, groundbreaking location where a lot of work has been done to give us a lot of the things that we take for granted today, the graphical user interface, the mouse, things like that. Okay, Bjorn Strustrup, the inventor of C++, looked at Smalltalk, said, yeah, great, wonderful language, but, hey, you know, C was dominant in industry. And C was not object-oriented, so we better get some object-oriented features into a version of C, and you've, whimsically added the plus because that's the increment operator in C, and voila, we have C++. And then Sun, another big player in the industry, big survivor in the industry still, decided that they would produce a language. The original concept was a language that was going to be called Oak and primarily designed to be put in smart devices, okay, like smart cell phones and things like that. But later on, it had a life of its own, became a mainstream programming language. You all know about it. Java, basically 1995 time frame, hit the streets and has taken off since then. So very recent, really.
I thought Oak was an academic program.
Well, my understanding is that people in Sun were involved with it, at least. We can check the actual details again if we want, but that's my understanding. A lot of projects in software and computing are partly academic and partly industrial. This relationship, but we'll have to check our facts on that one. Okay. One of the first things that you need to have as a skill when you're using Java is to properly use the JavaDoc facilities. This is a wonderful innovation that Java has made mainstream. And one of the things I provided in this course, right on the website, is JavaDoc for all of the code that is provided for you as you're working in it. And you should be thoroughly familiar with using JavaDoc to look things up. One of the things you have to be able to do is quickly take a look and understand which methods you can call in a class, including the ones that are in that class and the ones that are inherited. And because class hierarchies can get complex, having an efficient way to navigate around the hierarchies, the specifications of the hierarchies is important, and that's why the hypertext document that is JavaDoc is important. So get used to that. You can't expect to ever hope to memorize everything. Okay? It's not expected. You don't memorize libraries. Libraries are too big to memorize. You become familiar with libraries, and you become adept at quickly looking up details that you don't know. Okay? So in this course, I expect you to spend a considerable amount of time browsing through the JavaDoc of the core Java libraries as well as the libraries that we provide. you can search the code as well. You can look at the actual code for our libraries, the Simple Chat and the OCSF system, and the postal code system, and so on. But JavaDoc should be your first place to look, because it gives you the specification. It gives you an abstract view without having to look at the code. Then you can look at the code if you want to get a deeper understanding. Okay, so now we're going to remind you about a few Java slides, Java concepts. If you're weak in Java or don't have a Java background, have a C++ background, for example, I know one or two students here have that, there are some pointers on the website to decent references. There's some online tutorials, one provided by Sun, a few others. Which book should I look at? You might ask. Go to a bookstore and browse and get a book that you think that you can get through and understand. Okay, that's at your level. I won't make any recommendations, although there are a few on the website. There are plenty of books out there. Okay, so first of all, let's just talk about characters and strings for a few seconds, because we'll be using characters and we'll be using strings. It's important to understand what they are. In traditional computing, a string has been just a sequence of bytes representing 8-bit ASCII characters, but in Java, things are a bit more complex. In Java, the characters are not just 8-bit bytes representing ASCII characters. They are designed to represent Unicode characters, and Unicode is a more sophisticated language which encompasses the ASCII, which are the basic Latin characters and special characters and so on, but also the languages of all the countries in the world, including a lot of extinct languages and a lot of languages which are not human languages, like music, the languages of music, for example. There's symbols for all of those kinds of things too, and languages of other branches of science and mathematical symbols and things like that. Okay, so these are the characters that are stored in the Java strings, and they might be more than 1 byte. Okay, so one of the things you have to realize is that there's a thing in Java called a byte array, and then there's a thing in Java called a string, and just make sure that you understand that. Also understand the notion of what is a primitive. Char, C-H-A-R, is one of the Java primitives, okay, that stores a Unicode character. There's also a primitive byte, which stores an 8-bit byte, which, generally speaking, should not be used to represent character data like letters and numbers, unless you're doing some kind of internal coding. Anytime you expect to present information to end users, always use the full characters and the full Java strings, okay? Because if you use byte arrays and bytes, you're not allowing for proper internationalization. You're restricting yourself to a subset of Latin languages, and that's not considered desirable in today's world. Notice this class, character uppercase C fully spelled out with every letter. That is a class. Char is the primitive. Okay? Capital C, we said capital means class, right? And lowercase means not a class. Okay? In this case, it's a primitive. Lowercase is also used for variables. Important to understand the distinction. You will encounter bugs. I guarantee it in this course. You will encounter bugs that are based on the fact that you get an object character, or maybe an object integer, or an object float, when what you really want to process is a primitive, or vice versa. And so be aware of the potential for those kinds of bugs. It's one of the complexities in Java that's a little bit unfortunate. The Smalltalk programming language doesn't have that complexity, and the Smalltalk predates Java, but when they decided they wanted to introduce OO into C++ and then carry most of the C++ concepts through to Java, they left this kind of distinction between the primitives and the objects for these kinds of things, and can cause some grief. So be careful. The class character is useful when you want to call methods on the class. The char is useful when you want highly efficient kinds of processing. Okay? And string, notice the S. So it's a class, but it's actually a special class in Java. It's a built-in class in Java that, yes, it contains sequences of characters, but it's built deeply into the virtual machine that runs Java, and in particular, there's certain operators like the plus operator that are specially overloaded to work with strings. Okay, C++ has operator overloading everywhere, and you can do all kinds of programming with operator overloading, and you can use the plus symbol wherever you feel like. In Java, you can't do that because they found that that was too complex, but there are a few cases, and here's a particular case where there's built-in operator overloading. Plus is the concatenation operator for strings. Okay, arrays and collections. Arrays are another one of these special built-in classes, capital A, that are designed to be able to manipulate sequences of arbitrary Java things, objects or primitives. Okay? A fixed size. So if you're programming something and you want something that you absolutely know will be of a certain size, like 5 or 10, then by all means use an array. Arrays are efficient ways of having sequences of objects or sequences of primitives. But beware. Generally speaking, if you use arrays in arbitrary software development and you say there's going to be 5 of these things and there's only going to be 5, you're opening yourself up for inflexibility. Okay? There's been huge amounts of maintenance work that go on in the world where somebody says, okay, when we originally designed the system, there are going to be 5 levels of management in this organization. And so we're going to have an array of size 5 to capture some aspect of that. But then somebody decides they're going to add a 6th level. So you've got to change all your code and make these arrays now 6 long, and that becomes a pain in the neck. And so we try and stay away from, where possible, situations where we have to fix the size. And that's why we want to be a little bit wary of using arrays. And personally, I suggest that you use classes that are built into Java that are a bit less efficient in many cases, but add more flexibility. And often the flexibility is more than pays off for the efficiency cost. There are 2 classes. In the original Java, there was a class called Vector, which is still widely used. There's also a class called ArrayList, okay, which has much of the same functionality as Vector. I'll let you look those up on your own. Okay? These are classes that you should use instead of arrays anytime you think that there's a possibility that you don't want to put a fixed upper size on something. Either a fixed number or a fixed maximum. Don't do it because you end up restricting flexibility. Vectors and ArrayLists will grow in size as needed, and that's much more flexible. When you're manipulating objects that are collections, you have to be able to iterate through them. And there's several ways of doing that. You can use a for loop. For, I equals 1, I less than maximum size, I plus plus, loop through. That's one way of doing it. The other way, while loops can be used too. The other way of doing it is to use special classes, either called iterators or enumerations. Iterators is the one that should use now. It came out in a more recent version of Java. And the iterator, the code for the iterator is shown at the bottom of slide 34. I won't look at it. But the point is that with iterators, you have fewer chances of making bugs. You don't have to have logic that says less than maximum, and then you get the maximum wrong, or greater than minimum, or greater than equal to minimum, and you get that numbers wrong. So you're less likely to have bugs which mean you accidentally skip the beginning or end, or accidentally try and overflow the collection. They automatically deliver to you an element at a time, so you can loop through in a way that's more flexible. Less efficient, but more flexible. So again, we want to use classes like Vector and ArrayList for flexibility. We want to use iterators for more flexibility, as opposed to hard coding loops on arrays. Okay? Casting is a concept that has been the bane of C and C++ developers, especially C++. The rules of casting can really tie you in knots. Java has casting as well. The concept of casting is you have a return value from a function typically. You know what object it's going to be, that the variable is declared as something higher in the hierarchy. So I have a variable that is declared as type shape 2D, but I know, because of the logic of the system, that it's going to be a polygon. So I cast it to polygon, and then I can invoke the polygon-specific methods on it. Okay, you get an error if you fail to successfully cast. If in fact you had a circle, you try to cast it to polygon, it'll fail. Okay. So there's a number of rules about that described on this slide. I'll let you take a look at those yourself in detail. But the key idea is the second bullet: if you know an instance of a subclass is stored, then you can cast the variable to that subclass. Okay. Often used when dealing with collections. So if I know a vector contains instances of string, a vector is a class that can contain arbitrary sequences of any kind of object. But if you know that your logic has only put strings in that vector, and then you want to be able to do string operations as you iterate through a vector of strings, then you cast the result of the iteration to string, and then you can, given the expression shown at the bottom here, you can then invoke methods, or you can assign it to a string variable. You can invoke methods on the result of this expression to do things that are string specific. So you will need to do casting, and you will probably run into some bugs with inappropriate casting, but it's an important facility in particularly this kind of circumstance. Exceptions are another critical thing that you need to understand. Basically speaking, in Java, any time that you anticipate something could go wrong, you need to set up a try-catch block, as shown here, in order to be able to deal with that. So in the try block, I have execution of some code which can raise an exception, and in the catch block, I have code that will handle, in this particular case, an arithmetic exception. And it will do the alternative thing. Maybe raise an error message, maybe try an alternative algorithm. It's up to you, but do something. You can have many catch blocks to catch different exceptions, and the exceptions themselves form an inheritance hierarchy. Okay, so that you can catch higher level exceptions and that encompass any of the lower level different types of exceptions. Make sure that you understand these principles of exceptions when you're going to be programming in Java. Interfaces. Okay? Make sure that you understand the concept of interface. An interface is like a class, often called an abstract data type in actual fact. And what it does is it's like an abstract class that only has a set of abstract methods in it. Okay? The idea is that you can then, in any class in the system, you can say that that class is going to implement a given interface, and then you have to provide the concrete methods in that class or some subclass. So it works very much like abstract classes. A key difference is that whereas a class can only be a subclass of one other class, it can implement any number of interfaces. And that means that you have interfaces have a power that classes on their own don't have. And you can declare a variable to be of type an interface, which means that then you can put in that variable instances of any class that implement that interface. The only drawback is that then you can only call methods on that variable that are listed in that interface's definition, unless you cast whatever's in that variable to a class that you know it happens to be. Built into Java are a number of very important interfaces. Runnable, that has to do with threads. We'll talk about that in some detail. Collection, which is the interface that provides generic facilities that iterators work on. So, for example, vector is a kind of collection. Iterator itself is a kind of interface. You use it like a class. You don't even need to really know that it's an interface, but it is. You just get an iterator back from a function call. Comparable is another one. Basically says that you can do some less than, greater than operations on this. Clonable says you can make a copy. Okay. What we're going to do is we're going to leave it at that point today, and we're going to finish off the Java stuff next lecture, and then we'll continue with Chapter 3 next lecture as well.